Okay, a little bit better. Okay, why don't we get started? So my name is Mike Boyer, and today we'll talk a little bit about imaging atoms. Questions at any point, please interrupt me. Happy to answer them. Okay, so ultimately the goal of the class today, if things work out well, we'll see atoms. Let's talk a little bit about how we can image them. And actually, before we image atoms, let's talk about the size of an atom. So when we talk about sizes of atoms, we usually talk about them in terms of a meter, some fraction of a meter. So what is a meter? How large is a meter? Something like this, this, this. Any rough feeling for the size of a meter? Okay, exactly. It's roughly like this. So here, I bring in a meter stick so we can see exactly how long a meter is, but exactly, it's fairly large. So what happens, say you wanted to see something on a much smaller scale, what might you do? Biology class, for example. Sometimes you utilize something to look at things on a much smaller scale. Okay, microscope, an optical microscope. And in an optical microscope, you can get down to the size of bacteria, so you can image very small things. And about the limit of a microscope is a micron. What is a micron? Do you know what a micron is? Good. It's a millionth of a meter. So a micron actually is 10 to the minus 6 meters. But basically, it's take this meter stick, break it up into a million parts, and each part of one of those million parts is basically the size of bacterium, or a micron. So, exactly. And here's an image of bacteria from an optical microscope, and this is the length scale of each one of these is 10 microns here. So these are fairly larger bacteria, but again, something that can easily be seen with an optical microscope. Now, if we want to go even smaller, so atoms, considerably smaller than bacteria, we need to utilize other techniques. So an optical microscope can't see atoms. But if you use something called a scanning tunneling microscope, then you can see the atomic structure of materials. And so we say in atoms on the order of the size of an angstrom. What an angstrom is?
10.
It's actually even more. So it's 10 to the minus 10 meters. It's actually 10 billionths of a meter. So again, take this meter stick, break it up into 10 billion parts now. That's roughly the size of an atom. So we're getting very, very small here. But as small as it is, we can still actually image these. So here, this is an image taken by a microscope in my laboratory of a fairly complex compound. So I'll just say what each of the elements are: lead, bismuth, strontium, copper, oxide. There are reasons why I'm interested in that. But this is a scan of 180 angstroms. So this A here is our symbol for angstroms. And you can see the atomic locations in the structure. And you can actually differentiate these bright atoms, which are actually lead atoms, from these other, I guess, bluer atoms that are the bismuth atoms. So the color, this is just, I like the blue and white color, make it pretty, but it's not that we're actually saying the atoms are blue or white, it's just the color scheme I have here. But based on this color scheme, we can definitely pick out different types of atoms from our image. So I want to talk a little bit about how an STM works. So scanning tunneling microscope, it's a little bit of a mouthful to say. So we often will say STM to represent the scanning tunneling microscope. I want to talk about how it works, and it gets down to classical physics versus quantum physics. Classical physics, that's what dictates large objects. So your car, yourself. I pick up this ball. It's a large ball. This is what we say is a macroscopic object or a large object. And if I take a ball and I were to throw it against the wall, what's going to happen?
Bounce back.
Okay, it's going to bounce back. So we can confirm that's going to happen. Throw it against the wall, it bounced back. Okay? What happens if I want to get it to the other side of the barrier? Okay, I need to throw it over. So I need to throw it a little bit harder, give it a little bit more energy so that I can toss it over the barrier. So in classical physics, the only way for an object to go through what we call a barrier, a wall, is for it to go over it. You have to give it enough energy that it can go over it. Quantum mechanics, something different occurs. So in quantum physics, now we're talking instead about large objects, very small objects. Atoms, molecules, electrons, neutrons, protons. So here, I'm going to talk about an electron because actually electrons are what are relevant to scanning tunneling microscopes. If we have an electron incident on a barrier, it turns out in quantum mechanics there's a small probability that the electron can actually pass through that barrier. So if you have a huge number of electrons, most of those electrons actually will be reflected back, but a tiny fraction of them will actually pass through. So no matter, I mean, if I had 100 of these rubber balls and I threw them against that wall, I had 1 million of them, they will always bounce back. But if we go on a very small scale, like an electron, there's always a small probability that it can actually go through. And that's actually the crucial idea to how a scanning tunneling microscope works. So, draw another analogy. Okay, I have a battery and a light bulb. If I want that light bulb to light, so here's the series of batteries. I have a light bulb. And I want this to light, what do I have to do? I have to connect it. So if it's not connected, this isn't going to light up. And when I connect it, what's happening? Completing the circuit, and once I complete a circuit, what can happen? Okay, good. You have, we say sometimes current flowing, but what we mean is that we have electrons that can flow through the circuit. Electrons will not flow unless we complete that circuit. Unless you're talking about quantum mechanics. So in quantum mechanics, we have something very similar. Here, so this is a scanning tunneling microscope. We have an atomically sharp tip. It's a metal. You can think of it as just one of these wires here. We have an atomically flat surface. I'll talk a little bit downstairs about how you can get an atomically flat surface. And we bring that tip very close to that sample. So 5 to 10 angstroms away. So in other words, what we're saying is that they're not actually touching. We can actually fit a couple of atoms between the surface and the tip. And if we apply a voltage, so we hook up a battery, due to quantum mechanics, even though the tip and the sample are not touching, you can have electrons flow. Because what we're saying is that this region between the tip and the sample, that is that barrier that we were talking about. And that there's a very small probability that an electron can, what we say, tunnel from the tip into the sample. So because it's a small probability, you get very small currents. So just to give you an idea, the currents we're dealing with here are roughly 1 billion times smaller than a current that goes through a regular light bulb. So absolutely tiny currents. Okay, so that's how tunneling occurs. STM is scanning tunneling microscopy. So what we actually do is add a few more things to this system. So here, this is biased, but just think of this is our battery. We're applying a voltage to the sample. So now there's a voltage between the tip and the sample, and we can have electrons flow. We can measure a current. We can measure exactly what that current is. But then we add this one other aspect here, which is a scanner. So it's made out of a piezoelectric material. I don't know if you've ever heard of a piezoelectric material. It's a material that when you apply a voltage to it, it will move back and forth. It will shear one direction or distort in one direction. So you can actually apply, in a very controlled fashion, voltages on your scanner to move your tip across the sample and actually scan across your sample. Now the main idea is that the current depends on your tip sample separation. So if this is my tip and this is my sample, if I bring my tip back further away, the current's going to go down. So when I'm scanning over my sample, well, you have rises and falls due to the atomic structure. So if your tip is over the top of an atom, you're going to have a high current because the tip sample separation is larger than if you're between atoms. And so what this plot is up here is just telling you across your sample, how does that current vary? A bright region, which represents, for example, an atomic location, there's a lot of current flowing. And so that's a region of high current. Whereas between the atoms is a dark region, there's less current flowing. And so that's exactly how all we're doing is plotting the tunneling current as we scan our tip across the sample, and that tells us where our atoms are. Any questions so far? Okay, so let me show you a couple images. So on the left, this is a silicon 111 surface. So it's just the surface of the element silicon. And on the right is a material called niobium diselenide. Again, in each case, when we're imaging these structures, we see the atomic structure of these materials. And you can see I put atomic in quotes, just because I want to emphasize what you're really sensitive to are electrons. Electrons often like to stay around the atoms, so the nuclei. So here, each of these regions represents where an atom actually is. But we only know the atom's there because we detected electrons. There are other situations where you don't see atoms, and this is, I'll say this is one of my favorite images. This is a copper surface, and just to give you a scale, this is roughly 1 copper atom tall, and this is 3 copper atoms tall. In quantum mechanics, we say that electrons, they're particles, they have mass. But we also say in quantum mechanics that they have wave-like properties. That's just something that, that's one of the foundations of quantum mechanics, but it's a bit odd to say I have a particle, it acts like a particle, it also acts like water waves, for example. But I think it's comforting that we say that, but that we can actually see that. So here what we actually see are standing waves of electrons. So it's as if, this almost looks like a little bit of a waterfall, and you have ripples, on some lake. And over here, this is actually a carbon monoxide molecule, and it's as if you just dropped a pebble into your pond and you see ripples coming out from that. So again, these are electron waves that we see, as opposed to electrons wanting to localize at specific atomic locations. And then you can have fun. So you can use a scanning tunneling microscope tip to actually interact with atoms and drag them across your surface. So not surprisingly, one of the first people to do this, or groups to do this, worked for IBM. They wrote their own company name up there. But you can make all sorts of patterns and do, if you want, interesting physics. So this is moving iron atoms on a copper surface. They just made a circle of the iron atoms, and they called it a quantum corral. What they're doing was corralling electrons in that circle. And again, what you see are these ripples showing that you have electron waves. Okay, and the very last thing I want to talk about before we go downstairs is how do we actually do this. So we talked a little bit about the setup for the microscope, but there's more that's involved with that. So here's a microscope that I built when I was a graduate student back in the day. The major aspect, so first it looks huge, but it's actually about 3 inches tall and 2 inches in diameter, so it's pretty small. And actually, the one that we'll use downstairs is even a little bit smaller. But the major aspects are the same for all these microscopes. You have a region where you put your sample, so here we have a top-loading sample, and then you can see the tip right here. And then all the wires that you can't see are related to bringing the tip toward the sample, applying a voltage between the tip and the sample, measuring a current, and scanning the tip across the sample. So it's a fairly simple setup in some ways. The last aspect is we need to reduce vibrations. So you can imagine you bring a tip very close to your sample, you're 5–10 inches away, so a diameter of a couple atoms away, and you have vibrations, boom, you're going to crash your tip right into your sample. So what you try and do is try and reduce those vibrations. And vibrations have several sources. My lab's on the first floor, there's a road right by it. You have a truck drive by my lab, sometimes you can feel some of the vibrations in the floor. So one of the things that we wanted to do is try and reduce any of those vibrations originating in the floor from getting up to our microscope and ultimately getting to our tip and our sample. So the first thing that we did was we poured 2,400 pounds of concrete, which I'm sure my students were thrilled about, but into this frame here. And so again, a massive frame. Hopefully with a massive frame, you'll reduce vibrations that originate on the bottom, for example. And then we put them on a series of springs. So again, vibrations, more difficult to go through springs. And so now anything I put on here has at least been somewhat isolated from any vibrations on the floor. Finally, there are also vibrations in the air. So for example, when I'm talking to you, the reason why you can hear my voice is because of sound waves, pressure pulses that travel in the air. So I want to reduce those vibrations in the air. I want my students to be able to work in the laboratory but still take measurements. So the other aspect and everything that you see in the back there was to build an acoustic isolation room. So we have fiberglass insulation, sheetrock, and what we did was we built basically, if you've ever seen a music studio, exactly the same idea for a sound room. We built a room within a room. So there was an inner room, there's an outer room, and they're separated by a gap. So there's no direct connection. We put up fiberglass insulation, we laid some sheetrock, and then ultimately we put our experimental setup in here. So our microscope is inside here. It sits on the spring system, and it sits inside an isolation room that we can close up and we can control everything from outside. So trying to do as much as possible to reduce the vibrations. So why don't we go downstairs, take a look at, it's actually a somewhat different setup we have here, but the features are the same, and let's see if we can actually image atoms.